Hi everyone, my name's Rilian Windsor, and I will be presenting our new paper, A Convolutional Approach to Vertebra Detection and Labelling in Whole Spine Magnetic Resonance Imaging. In this talk we consider two tasks, that of vertebral body detection and that of vertebral body labelling. For the first task we mean, given a sagittally sliced spinal magnetic resonance image, can we detect and bound all the visible vertebral bodies in 3D? For the second task, can we determine which vertebral levels these detections correspond to? We present two new contributions in this talk, one to each task. For the first task we propose vector field regression, a novel method which allows us to detect vertebrae from a range of different fields of view in an expressive and flexible manner. For the second task we propose a new method of labelling detected vertebral bodies inspired by language modelling, improving on simply counting up from the bottom vertebra. As we present two new related but distinct contributions, this talk is broken into three parts. One section to give an overview to each contribution, and a further section discussing experimental results. We begin by talking about vector field regression, our new method to detect vertebrae agnostic to their level. Here we can see a vertebra across a subsample of sagittal slices. How could this vertebra be represented in 3D? In this method, we consider it to be a series of quadrilaterals through the slices, with quadrilaterals present in slices where the vertebra is present, and absent in the slices where it is not. We can detect the vertebra by finding the vertices of the quadrilaterals in each slice, and then grouping those detected vertices into a series of quadrilaterals. Finally, the quadrilaterals are grouped across sagittal slices to form 3D volumes bounding each vertebra. The first step is detecting these vertices. This can be done by training a network to produce a Gaussian peak over each vertex. We use a VGG net with 5 detection channels to achieve this task. The first 4 channels detect each of the 4 corners of the vertebra. A 5th channel is added to detect the centre of each vertebra, and this is used later to group each detected vertex into a quadrilateral. Once these Gaussian peaks have been produced, we can find local maxima within each detection channel to find the individual points of the vertices. By applying this network, we have detected the 4 corners of each vertebra in each slice. The question is then how to group these corners into quadrilaterals. We could use heuristic methods, such as assigning a corner to the closest centre detected. However, this fails in cases of extreme curvature or abnormally shaped vertebrae. Our solution to this task is to predict 4 vector fields corresponding to each corner type. At the locus of each vertex detection, the corresponding vector field should point to the centre of that vertebra. This allows us to be robust to flips and rotations, meaning grouping is fast. Here we can see one of 4 predicted vector fields. At each point of each vertebra vertex, the corresponding field points to the vertebra centroid, indicating to which vertebra that vertex belongs. Therefore, our full network has 13 output channels, 5 detection channels and 8 channels responsible for predicting these 4 vector fields. This gives us vectors corresponding to each corner detection. Grouping is then as simple as assigning each centroid detected the 4 corners of each type which point closest. In practice, we add extra robustness checks to avoid spurious detections, and the details of these can be read in the full paper. At this point, we have detected quadrilaterals corresponding to each vertebra in each slice. We must now group these detections across sagittal slices. This is simply done by grouping quadrilaterals across slices if their intersection over union is greater than 0.5. We will now move on to the second contribution of this paper, where we determine the vertebral level corresponding to our detections. However, before delving into the method, I'd like to first outline why we require a more sophisticated solution than simply counting up from the bottom vertebra. Firstly, this simple method would assume that each vertebra in the spinal column has been detected. It also assumes a fixed anchor vertebra, for example S1 at the bottom of the scan, or C2 at the top. In the example image here, neither such vertebra is visible. Finally, it cannot deal with a variable number of vertebrae in the spinal column. In practice, around 10% of patients will have one more or one less vertebra from S1 to C2. We consider two types of information when labelling a vertebra: its appearance and its context. Appearance features refers to all local information about that vertebra, such as its size relative to nearby anatomy, shape, and rotation. Context information refers to information given by our predictions for the surrounding vertebra, and thus constitutes a joint probability over a sequence of detections. The first part of our method considers appearance alone. We extract a 3D volume surrounding each detection and attempt to determine the level of that vertebra from the volume alone using a simple 3D convolutional appearance network. Here we see a detection of an L5 vertebra assigned a 47% probability of being L5 and a 32% probability of S1 based on appearance alone. These predictions based on appearance alone act as a prior on each detection. They are used to construct an input height level probability map. This tells us the probability of a given vertebral level at a certain height in the image. To construct the input map, the output probabilities from the appearance network are assigned at heights corresponding to the detection. A UNet context network then performs image-to-image translation, updating and refining the input height level probability map, taking into account the appearance alone based probabilities of nearby detections. This produces a posterior height level map. The final step is to decode this continuous posterior height level probability map into a discrete vertebral sequence. We sample the map at discrete heights of the detections. This gives us a probability for each vertebral level for each detection. However, instead of greedily taking the argmax of each probability vector, we wish to find a sequence which obeys constraints, such as no repeated vertebrae, and that the thoracic spine appears above the lumbar spine in the image. Here we take inspiration from language modelling and use a beam search. As well as generating several possible candidates for labelling a sequence, this also allows us to build in constraints. The exact details of the beam search we use are in the paper. Having covered both our contributions, we will now show some of the results of these methods combined across a range of datasets. We use 3 datasets in practice. Oxford whole spine consists of clinical whole spine sagittal magnetic resonance scans. We split this into training and testing sets. The detection, appearance, and context networks are all trained separately, and the resulting pipeline is assessed on the testing set, as well as 2 mostly lumbar datasets used in previous works, Genodisc and Zukić. Here are some example results of detection and labelling overlaid on the mid-sagittal slice of the Oxford whole spine test dataset. We also saw near-perfect results on lumbar scans. Here are examples from the Zukić dataset, and here are examples from the Genodisc dataset. These plots are errors, so lower is better. Quantitative evaluation shows that our vector field regression significantly improves on previous fully automated methods of vertebra detection in lumbar scans for the datasets used, and matches semi-automated methods of vertebra detection in whole spine scans. Our labelling method also exceeds performance of previous methods for labelling vertebrae in lumbar scans. We also implemented a bidirectional LSTM operating on the probabilities extracted from each detection by the appearance network as a baseline, and we exceed performance of this. Finally, we show examples of our network dealing with in-the-wild pathology, such as fused vertebra, hemivertebra, and extravertebra. This suggests that this method is an appropriate candidate for clinical use. In the paper, we also demonstrate a potential application of the pipeline for scoliosis detection. This concludes our talk. For more information and greater detail on both the method and extended results, please consult the conference paper or the extended version available on arXiv.